All right, hello everyone, welcome back. So go ahead and turn on your webcams. Remember, the visual presence is required for the attendance. All right. So as I mentioned last time, I'm always going to start with taking attendance. So I will waiting for one more students to join in, and then I'm going to go ahead and start. All right. So We have few new students. All right. So again, apologize if I mispronounce your name. Feel free to correct me. Essa El Hadri.
Yes.
Okay. I think Mohammed Amiri.
Here.
Okay. Zaida Vargas Betancourt. Is Zaida here? All right. I didn't hear anything from Zaida. All right. Not here then. Charles Chilaka.
Here.
All right. Natalie Elizararas.
Here.
All right. Andres Garcia.
Here.
Okay. Joseph Garcia.
Here.
All right. Thank you. Garza.
Here.
All right. So your name is David then? David Garza?
Yeah.
All right. So because it's here it just says Garza. So that's why. So all right. So you're David then. Good. Jose Gonzalez. Jose Gonzalez. All right. Not here, I guess. Daniel Gregoriona.
I'm here.
All right. Dean Kessler.
Here.
All right. Dylan Kawashiri.
Here.
All right. Zana Keating.
Here.
All right. Benjamin Shirani Lapari.
Here.
Excellent. Sarah Lee.
Here.
Okay. Stevie Littleton.
Here.
All right. Thank you. Tyler Medina.
Here.
Okay. Gia Mitchell. All right. Gia Mitchell. All right, then, not here. Winifred Olive.
Here.
All right. Jose Orozco.
Here.
Okay. Long Fan.
Here.
Thank you. Iris Cuema. Iris Cuema. All right. The student was not here on Monday as well, so probably will be dropped. Oscar Ravshenbekov. Oscar. All right, not here. Jose Rodriguez.
Here.
All right. Angel Sanchez.
Here.
All right. Marcelo Sanchez.
Here.
Francisco Serrano. Francisco Serrano. All right, I guess not here. Noel Serrano.
Here.
All right. Jacob Sola.
Here.
Okay. Arsani Soleiman.
Here.
All right. Devante Thornton. Devante Thornton. All right, not here then. And Ricardo Villacana.
Here.
All right. So I think someone just came in. Was it Jose Gonzalez? Are you here?
Yes.
All right. You just made it. All right, guys. Thank you. So so then let's go ahead and start with today's class. So basically, we have lab 1 that was due today. So I'm gonna then talk about Lab 2, which is on Pivot Interactive. So hopefully you guys had a chance to go and register with Pivot Interactive. And if you didn't, it's okay. So you guys still can go and do it, let's say today. This lab will be due on Saturday midnight. So you have, a few days to work on that. So I'm going to then give you a brief, sort of like, let's say, overview of the theory behind today's lab. And then we're going to do, introduction to Pivot Interactive. I'm going to give you introduction to the platform and the steps needed to take the experimental data and do the experiment. So feel free to stop me anytime and ask me questions and things like that. And then we're going to talk about, and we're going to do the, let's say, recitation 2, which will be based on chapters 2 and 3. And it's going to be due, I think I have this due on Friday midnight. So because remember, so I'm not going to see you until Monday. That means, Monday when we meet already, the chapter of the week is sort of like chapter 3 and chapter 4. So like, let's say actually. So when we meet on Monday, the recitation then will be on chapter 3 and 4. Okay. That means I'm including some of the chapter 3 questions on this recitation. So you can do chapter 2 questions right now today during the meeting, right? During the, let's say, breakout session. If you're already ahead and already covered, let's say, chapter 3, you can also work on that. If not, basically just do whatever you can. And you have, like, let's say, 2 more days to learn about the chapter 3 concept and then, finish the recitations. All right. So, and I'm going to most likely, I don't know, let me see. All right. So Paula is not here yet. So I'm going to introduce you to Paula. She's going to be the embedded tutor for this class. And I believe she already announced her schedule. I believe she's going to be tutoring from 2 to 4, Monday through Thursday. That means every day before the class, right, before our meeting, including Tuesday and Thursday, you can go to the Valley Tutoring Center and get help from her. She can help you with the lab. She can help you with the, let's say, homework, things like that. And she's always also going to be present during our recitations going forward. So then let's say I'm going to rotate her from group to group. So let's say 10 minutes with one group, 10 minutes with another group and things like that. And you guys can talk to each other, help each other, and also, get help from her and get help from me during the recitations. Right. Any questions? Okay. So then, let's see. I'm waiting for the whiteboard to open. All right. All right, guys. So this lab 2, basically gives you an experiment on one-dimensional motion along a ramp, on a ramp. Okay. So let's see. All right. All right. So I got a couple of questions. So one of them is in terms of the recitation 1 key. I'm not going to post the recitation 1 key simply because most of those questions is just basically units and things like that. So, but I do have recitation, and I mentioned that from last time. Going forward from recitation 2 and onward, right? I'm going to be then posting the answer keys. That means whenever you're doing the recitation, you're already given the answer key. Your goal is to learn how to solve the problem, how to organize your work, solve the problem, and then verify that with the key. Because this is where kind of like the physics starts. You're going to be then solving problems using kinematic equations and things like that. So when you're doing the peer review, right, you want to pay attention to that. By the way, the peer review going to be available already for the recitation 1. So I'm going to give you a day or 2 to work on that. So make sure that you guys do the peer review. Each one of you going to get 2 peer review, and it's anonymous. That means whoever you're reviewing, they're not going to know who's reviewing. That means, you're going to have anonymous peer review. So try to be, try to provide, some kind of, feedback. If you think that, there's a feedback that you can provide that can help the student to better do the, problems and things like that, go for it. And don't forget to provide also a grade in a comment. So let's say all the recitations are 5 points. So let's say if all the work is there, everything is good, like 5 out of 5. I keep forgetting. I'm going to put a rubric for that, so you guys sort of like more or less know how to provide that, grade. But you can see if all the work is there, all the units and like let's say answers box and everything like that, then it's like 5 out of 5. Missing one problem, then 4 out of 5, and so on and so forth. All right. So also in terms of the Zoom lecture that we had on Monday is posted already on Canvas, and the Zoom the Zoom meeting, right, that we have today will also be posted. And remember, there are no Zoom meetings for the lecture portion. Lecture portion is all online. So this is a not only, let's say, even in the regular semester, this is a hybrid class, which means that there were no face-to-face meetings for the lecture portion, only for the lab portion. All right, so then let's talk about lab 2. Okay, so the lab 2 basically talks about 1D kinematics. That means how to, let's say, understand one-dimensional motion and how to use the motion to, to do a graph, and how to interpret some of those graphs, how to linearize your graphs. So those are some of the things we're going to be looking at. That means we're going to look at, in terms of one-dimensional motion, how to graph position versus time, let's say data from that motion, and then how to linearize that graph, and how to do the velocity versus time graph. All right, so I'm going to start with the sort of like, let's say, very simple, scenario where you have a flat surface and you have an object, and I'm sure you guys learned in the lecture class, right, that we are looking at the particle model, which means that any object I can just represent it as a particle. Let's say here's the object, and I just represent with the particle, and then I want to have some kind of reference position, and that reference position most of the time can be the origin. So let's say I can say that this is x equals 0, and I want to indicate in which direction, let's say, is my positive x. So let's say then I can say this is a positive x direction. That means that when the object is moving to the right, then I can say the object is moving in a positive direction. If object is moving to the left, then object is moving in a negative direction, right? So let's say then I have an object that's going to be moving along the straight line, and it's going to be moving to the right. Okay. So now one thing I can do then, I can then take a timer, and then I can say that, all right, so at t equals 0, my position is x equals 0. And then as object moving to the right, I sort of like, let's say, measure its position as a function of time. That means maybe some later time, object reaches some, distance away from this, let's say, reference position, and then even further and further and further. But I want to take a data such that I can graph that. So then easiest thing to do here is to take measurements at some equal time intervals. That means you don't want to take a, position at t equals 0, then position at t equals 1 second, then position t equals 20 seconds. And, because the first measurement is 1 second interval, the second one is 19-second interval. So it's not going to give you much information. So then one thing we're going to do here, we're going to, start measuring such that every, let's say, measurement of distance has, equal time interval. So let's say t equals 1 second, t equals 2 seconds, t equals 3 seconds, t equals 4 seconds, and so on. That means, every 1 second, I'm going to measure the position of the object. And let's say what I do here is I'm going to see that, okay, so object is right here, an object is right there, an object is right here, an object is right there. Then I can say, all right, so this is then x1 at t equals 1. This is then x2, the position at t equals 2 seconds. This is then x3, position at t equals 3 seconds. This is then x4, t equals 4 seconds, and so on and so forth. That means I'm measuring the position. Imagine, right? The object is moving, and I'm kind of like, let's say, taking picture of the object. And if I put all those frames together, I get this image, sort of like, let's say, where object moving to the right, and each, let's say, frame represents its position every 1 second time interval. All right. Now, what I can do then with this is I can put it organize it in a table. I can say, all right, so then let's say this is my t, right, in, let's say, seconds, and this is my x in minutes, sorry, in meters. So then I can say, all right, so when object was 0 at time, t equals 0, right? At t equals 0, object was at the origin, so the position is 0. Okay. Then I'm going to say, all right, so I'm going to say then, all right, so let's say this is T1. I'm just going to write it in terms of T1. So let's say T1, T2, T3, right, and so on and so forth. Assuming that my time intervals are all the same, that means from T1, T2, T1 to T0 is 1 second. T2 to T1 is 1 second, and so on and so forth. Then I can say, all right, so then for T1, then I get X1. For T2, then I get X2. For T3, I get X3. And let's say so on and so forth. One thing I can do with this information, then I can plot position versus time graph. All right, so let me do a little better graph. All right, so let's say here's. All right, so this is position. That means X in meters versus time in seconds graph. And I'm going to start plotting that. So let's say putting the points. I have 0, 0. So let's say I have then 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Let's say something like that. Now, if I then plot this, for example, T1, X1, T2, X2, T3, X3, T4, X4, right? And something like this. So let's say I'm going to get this graph. Now, one of the things I can do here is I can find the, let's say, what we learned in the previous lab, right? Best fit line. And I'm going to get a, a graph like this. So this is, again, this is X versus T graph, position versus time. Now, who can tell me what type of motion then we have based on this graph? What did you guys learn in your lecture class? What type of motion do I have based on this graph?
Constant?
What do you mean
Uniform?
by, yes, not necessarily constant, but uniform. Exactly. So this is a uniform motion. All right, so who can explain what's a uniform motion? Why do you say it's a uniform? How do we know that? Remember, guys, there is no such thing as wrong answer. Just, if you say you're uniform, that means, you either guessed it or and just say it. So then everybody
The
else.
constant slope,
Constant slope.
like
Well,
the same amount of meters is moved per second, or not necessarily
exactly.
meters, but distance.
Yes. That's exactly what the uniform motion is in a way. That means if you come back and look at this, this is actually known, what I have over here, right? So this is actually known as a motion diagram. So motion diagram. Motion diagram is when you represent the position, as a particle, right? As a function of time, sort of like, let's say. And this is a position versus time graphs. So those are two different tools that you can use to understand motion. Now, the uniform motion is when if you measure this distance, so this is the distance between x1 and x0, and then this is then the distance between x2 and x1. That means you're talking about like delta x1, which is x1 minus x0, let's say, and then delta x2, which is x2 minus x1. then delta x3, which is x3 minus x2. That means I'm talking about this distance between each, let's say new point compared to the previous one. And one thing we have as a uniform is when all of those delta x's, right? Delta x1, delta x2, delta x3, they're all equal to one another. That means it covers same displacement, right? Or same distance for the each new time interval. That's how we know it's a uniform motion. And it's important because uniform motion can be identified by this, right? In terms of delta x1 and delta x2, and that means that the distance between each time interval is exactly the same. Also, we know that if I take the ratio of delta x over delta t, and this is my velocity, so if I do delta x1 over delta t, this is v1. If I do delta x2 over delta t, this is v2. Well, since delta x1 and delta x2 are the same and delta t's are the same, that means you can say those are also the same. That means v1 is equals to v2, equals v3, equals v4. And what you will get here is what we say constant. It's a constant velocity motion. So uniform motion is when your velocity is constant, which means you can say, right, it's constant because the displacements are constant. Now, whenever you're doing the plot for a constant velocity motion or a uniform motion, I prefer uniform motion. Whenever we're doing a graph for a uniform motion, it's always gonna look like this, basically a straight line. And whenever, let's say, I choose any 2 points on this line, so let's say I choose this point 1 and this point 2, and then if I do then the ratio of the rise, which is delta x, over run, which is delta t, see, I'm gonna get v. So the slope, the velocity is the slope of the position versus time graph. Remember, rise over run, right? We learned in lab 1. Well, rise is delta x, run is delta t, because it represents some delta t, this represents some delta x. Well, that's just the velocity. So the slope of this line is then the velocity. But see, if I choose another 2 points, let's say 3 and 4, and do the same thing, well, I'm gonna get the same exact velocity and same exact slope because it's a straight line. That means whenever you have a uniform motion, you can also identify uniform motion, or we call it linear motion, right? If your graph is a straight line. Well, in a way, what the linear means is that these two quantities, right, x and t, are linear with respect to one another. Because here's what I can do. See, if I take that equation for the slope, if I rearrange, I get this: delta x equals v times t. Oh, so v times delta t, which means delta x is directly proportional to delta t. So the linear relationship is when your x quantity and y quantity are directly proportional to one another. So that's why here delta x is directly proportional to delta t, and your graph is a straight line, and your velocity is constant. So basically, it's if you do y equals mx, delta x is the y-axis, delta t is the x-axis. See, the velocity is just your slope. All right, guys, by the way, feel free to always, ask questions or type it in the chat room. Now, next thing here is this. What if the object starts moving like this? So I'm going to do a motion diagram for another, object. So let's say here at t equals 0. And then I'm here, and I'm here, and I'm here. And let's say, and I'm here. So then if I do, like, let's say this is x0, this is x1, this is x2, this is x3, this is x4. So what do you guys notice here? This is, let's say this is T1, this is T2, T3, T4. So what do you guys notice here? There's different.
It's not uniform.
It's not uniform. Exactly. Then why do you say it's not uniform? Based on what?
Because the difference, the change in positions per time interval is different.
Exactly. Perfect. That means if I measure this delta x1, then measure this delta x2, then measure this delta x3, they're not the same, right? Clearly the distance at delta x3 is, bigger than delta x2, that bigger than delta x1, and so on and so forth. That means, this is non-uniform motion. It's not a non-uniform motion. Now, what I have here is then for non-uniform then is this, okay? So again, I can take this and put it in a, organize it in a table. So this is T in seconds, X in meters. So I'm gonna get, let's say T0, X0, T1, X1, T2, X2, T3, X3, right? The one thing I have now is this. If I do delta X1 over delta T to get V1, and if I do delta X2 over delta T2 to get V2, or, same way delta X3 over delta T to get V3, they're no longer the same. V3 is not equals to V2 is not equals to V1, right? Because then delta X1, delta X2, delta X3 are different. And since delta X3 is the longest distance, it's going to give me greater velocity. So then velocity 3 is greater than velocity 2. Velocity 2 is greater than velocity 1, which means that our velocity changes. And that's what non-uniform motion means. You have a changing velocity. Velocity changes as a function of time instead of staying constant. All right, now let's see how we can identify that in a graph. Okay, so if I do a graph like this, so who can help me? What type of graph should I get if I do X versus T?
An exponential graph?
Well, we usually call it parabolic. Yes, so it's going to be a parabola. So the graph is actually going to be something like this. All right, so this graph represents object increasing speed as it's going in a positive X direction. So this is the graph you're going to get. This increasing speed going in a positive X direction. Okay. So then equation representing this motion is no longer delta X equals V times delta T. Because delta X V times delta T assume that it's a straight line, basically a uniform motion. But now we don't, because now we know that there is a change in velocity, and this change in velocity is because of the acceleration. So this equation then becomes 1/2 a times t squared. So it's basically now based on this. So then this is your equation for, and this is then becomes your, initial velocity. That means your graph described with this equation. Now, assuming that at t equals 0, object was at rest, then this entire, term goes to 0. And then what you end up with this, delta X equals 1/2 times a times t squared. That means this is your equation. Now, does this equation describe the type of graph you have? What do you guys think? Because it's important not to just memorize things, but to understand why they are the way they are. So let's say looking at this equation that I have and looking at the graph that you have, does it make sense that the graph is the way it is?
Yes, because t is squared and it gives a parabola.
Exactly. Because looking at this equation, remember, you're plotting delta X versus T, but delta X is not directly proportional to t like in a previous, graph, where then you would have had the linear straight line, but it is not proportional to t squared. It's sort of like graphing y equals mx squared. Y equals x squared, right? That's basically nothing but parabola. That's because this is how the graph or how the delta x related. It's not proportional to t, it's proportional to t squared. Why? Because there's a change in velocity, because there's an acceleration in your system. And whenever there's an object, not basically whenever there's a non-uniform motion, delta x is no longer proportional to t. Delta x is proportional to t squared, assuming that, let's say, it starts from, initially starts from zero velocity. Okay, and this is your graph. Okay, now one of the things we're going to be then doing here is this. So let's say I want to use this data, basically the data for a non-uniform motion, but I do want to have, a straight line graph. That means I want to linearize. I want to linearize my graph. So how do I linearize my graph? Missing A over there. That means I want to still have a position and I want to still have a time, but I don't want to get a parabola. I want to get like a straight line. But I still have, I still have this equation. How would I plot this so that I get, all right, somebody said ln. No, it's not. So think like this. I have my delta x equals 1/2 at squared. I'm still plotting x and t because those are the things that I measure. But I want to get a straight line instead of parabola. How would I plot so that I get a straight line? What is delta x is directly proportional to? What do you
T
guys
squared.
think? What is it?
T squared.
T squared. Exactly. Do you guys agree that delta x, see, 1/2 a is actually proportionality constant. Delta x is directly proportional to t squared. That means if I do x versus t squared, then if I plot the same graph, but instead of x versus t, but do x versus t squared, I'm going to get a straight line. This is what we use for linearizing this graph, this data table. That means we are plotting position versus time square rather than position versus time. All right, so then question is, why do we need that? Well, for two reasons. Because which one do you guys think is easier to get the slope? This graph 1 or graph 2?
Graph 2.
2.
Graph 2, right? I can just choose any 2 points and find, let's say, the slope, and it's going to be constant, right? Doesn't matter which 2 points I choose, let's say. So the graph 2 is easier. And here's the thing. Once I find the slope of this graph, let's say slope, that means I am plotting this as y equals mx, right? What is my slope going to be then directly equals to? So let's say I'm using this, right? Y equals mx equation, basically. And I'm using this on equation 1/2 at squared. So what do you guys think? Once I find the slope, what can then slope allow me to find?
Acceleration.
Acceleration. Yes. See, if I'm plotting delta x on the y-axis, t squared on the x-axis, then anything that, let's say, proportionality constant, right, which is the slope, let's say here, is then it equals to 1/2 times acceleration. That means I take that slope, I double that, then I have my acceleration. See, that's how we can get the acceleration. That means this is the graphical way of finding the acceleration of your system, of the object, as it's moving, along the straight line. All right, any question about the difference between uniform, non-uniform, and of the graph of the uniform, non-uniform, and then how to linearize it? Any questions?
I have a question, Professor.
Go ahead.
Would it be possible to do the square root
of x and plot t?
Yes, definitely. Because, what you're doing here, you're just doing the square root of both sides. So yeah, you can do that. But obviously you're making it more difficult, right? So I imagine it's a little bit more difficult.
Right.
Okay.
Thank you.
Because then your slope is also then, square root of a, right? Square root of 1/2 a. So, but yes, it is definitely possible, of course. Okay. And we will be, doing something like that later on when we do, for example, work done is equals to 1/2 mv squared. So when you're doing work and v relationship, you can do work is directly proportional to v squared, or you can say square of work is proportional to v. Exactly that's what you just proposed. We can do that for that, particular. This is going to be, I think, lab 7 or 8. We'll get to that. All right. So what we're gonna do that for our lab though is slightly, make this interesting. That means we're gonna have an incline like this, and the theta represents the incline angle. And then we're gonna have an object starting from here, and then object gonna, move on a frictionless surface. That means as soon as you let go, it's gonna then start speeding up. Okay. Now then, here's what we have. What do you guys think? Let's say if the object is going down an incline, is this a one-dimensional motion or a two-dimensional motion?
Two-dimensional.
Dimensional.
Well, it is correct to say it's a two-dimensional if, let's say, I take this type of coordinate system. If I do this, then yes, object going down, cover x, y, and things like that. All right. But here's what we're going to do. We're going to make actually a modification to our coordinate system. Think like this. Our coordinate system right now has this theta, right? It has some angle theta with respect to the incline. What I'm going to do, I'm going to tilt it by this angle. That means think like this. So what I'm going to do here, I'm going to take my coordinate system. Okay. And I'm going to shift it such that my y-axis is perpendicular to the incline. This is my y-axis. And my x-axis is parallel to the incline. All right, so it's parallel to the incline. This is my x-axis. And if I do this, then as object going down an incline, so what type of motion is this now? One-dimensional or two-dimensional?
One-dimensional.
How do we know it's one-dimensional?
Because the motion is only on one axis.
Exactly. Object changes position only on x-axis, right? Basically, y-axis just basically remains the same value. And it's a very easy to just modify our coordinate system like this. Well, there's a trade-off, right? Then, for example, in acceleration, one thing you will learn here is going to be then equals to g sine theta, for example. This is something hopefully you can learn in your lecture class. But the idea here is that the acceleration becomes g sine theta. But still, it is constant, and the object as it's going down is just basically going to be pretty much a one-dimensional motion, even if it's going down an incline. Okay. So that means everything we just learned about doing the graph of a non-uniform motion along a straight line, and it is a straight line, right? It's not a curve, it's a ramp, but still, because of the coordinate system, it is a straight line motion. One thing we can do here is, for example, instead of, let's say, finding acceleration, something like this, which let's say we don't know right now, we're going to be able to then find the acceleration, as I just showed you, in terms of finding the slope of a position versus time graph, linearize the graph, and then find the slope, and then find the acceleration from the slope. That means what we can do here is we can say that this is x1, this is x2, this is x3, this is x4, this is x5, right? And measure the time. T0, T1, T2, well, let's say T1, T2, T3, T4, T5, right? And then take this and do the graph, okay? That means if I do this graph, I'm gonna get straight, same thing. If I do X versus T, well, the object is gonna slide down. That means it's gonna start speeding up. So then first, if I do X versus T, I'm gonna get a graph like this. But by changing this X versus T square, I can change the shape of my graph. I can get then a straight line by linearizing this. If I do versus T square. And if I find the slope of this graph of the, X versus T square, then as the equation showed over there, I'm looking at this relationship, delta X equals 1/2 AT squared, since V initial equals 0, then the slope is nothing but 1/2 times A. Then I can find the acceleration from the slope of the linearized graph. Okay. All right, any questions?
Professor, I have a question. Can you go over A equals G sine of theta one more time?
All right, so basically you don't really learn about that it's equals to A equals G sine theta until you learn about forces, because this equation comes from basically the fact that acceleration is due to the only gravitational force acting on it. So in a way, think like this. So here's the acceleration, like let's say this is G, which is the acceleration due to gravity. And then let's say this angle theta is the same as this angle theta over there. So then if I'm looking at the acceleration, so acceleration has two components. One component that is parallel to the surface, one that is perpendicular to the surface. One that is parallel is this one, which is opposite to this angle theta. So it becomes then G sine of theta, because it's a opposite component to that triangle. So it equals to G sine theta, where G is acceleration due to gravity, and equals to 9.8 meter per second squared. If you covered, or if you already went over the lecture notes or the lectures, for chapter 2, you have, at the end of chapter 2, then you talk about the acceleration due to gravity. But again, so let's say for our purpose, right, for our lab, you don't even need to know this equation. What we're doing, we're finding acceleration from the, position versus time graphs, let's say.
Thank you.
Sure. All right. So, and then one thing we can do here is we can use this to get the velocity versus time graph. And velocity versus time graph, then, for example, this is a non-uniform motion. And for the non-uniform motion, velocity changes. So, for example, for this graph, how can I find the velocity? What is the velocity, for example? How do we find the velocity for a non-uniform motion graph?
Take the derivative.
Yes, but like, let's say from the graphical point of view.
Slope?
Well, slope of this graph?
The slope of the tangent at the point that you're examining?
Exactly, perfect. Because remember, this is a non-uniform motion, which means velocity is not constant. At any time, velocity changes. So there is no such thing as one velocity. So what we do here, we choose some kind of time of interest, some instant of time, and then we draw a tangent line, find the slope of that tangent line, then that's an instantaneous velocity, VI, V instantaneous. And it is dx dt, yes, it is derivative, but let's say for us, instantaneous velocity is the tangent or the slope of the tangent. That means if I do this, I can then know what is the velocity at t1. So then I can put this, okay, at this time, here's the velocity. Then I go to t2. At t2, then I do a tangent and find the velocity at t2, the slope of that line. Then when t is 2, When t is 2, then I can find the v2, and so on and so forth. Then at t3, I can find v3, right? So let's say by going and looking at the t3, which is here t3, doing a tangent line and finding the slope of the tangent line. Right, so those are sort of like, let's say, the tools that you use to find the velocity, because this is not a straight line, right? So velocity is not, so let's say this graph, right, we can't really use for the velocity. We can use that for acceleration, but not velocity, because slope of this x versus t graph gives us acceleration. But if I come back to the x versus t, the parabola graph, I can use that to find velocity. Okay, and I will show you, let's say, when we go to the pivot. All right, any questions? Because I'm going to now go to the Pivot Interactive and show you the actual experiment. All right, so let me then go and all right, guys. So right now, if you already registered to Pivot Interactive, then you should be able to then see this lab 2. This lab 2 motion graphing on a dry ice pack on a ramp. So this will already be visible for you when you go to Pivot Interactive. Remember, I told you last time that you need to register for this, and the steps are on Canvas that I have, where it says the lab, introduction, right? So use that to enroll for this. So then let's say here's the lab. So the objective of this lab is to create and analyze position versus time graph for motion with non-constant velocity. That means a non-uniform motion. Learn to linearize data. Use this data to find mathematical relationship between position versus time for this motion. Create and interpret a velocity versus time graph. Okay. So, and then use the velocity versus time function to make prediction about the motion of the pipe. All right. So, and here's then what we have. So the Pivot Interactive Labs are sort of like a similar to Mastering Physics platform, that it allows you to not do an experiment, so like, let's say, but watch an experiment and make measurements. So you can't really do the experiment, but you can measure the experimental data and things like that. So here's sort of like, let's say, introductory part. They show you how they're using the dry ice. So they're making the surface as smooth as possible. Right, so now you have a basically perfectly frictionless, interaction. All right, so then we can look at an experiment where that same, dry ice pack is connected to some, support over there. It's under the top of a, frictionless incline. Okay. Now, what we're going to do here is we are given the mass. So let's say if you click here, change, you can see, right, you have different, information, right? Mass A, mass B. So, feel free just to, let's say I'm going to do right now, mass A and number 1. Okay, so then you just try to do something else, because, you don't want to use my, data points that I'm going to right now measure. So mass A number 1, you can use mass A number 2, mass A number 3, right? Whatever. So you can choose any of those things. So right now for the demo, I'm going to use mass A and number 1 ram angle. So that means you just do anything other than this combination. All right, so let's load. All right. So basically, I probably chose a very, small angle, but it's okay. So here's then what we have. Experiment is like this. So starting from rest, you can see, right? It is basically at rest right now. We cut the cord and then it starts speeding up down. Because it's frictionless, right? It's inclined, it's going to speed up until it reaches at the bottom. All right, so our goal will be to make measurements and fill out this table. So in this table, what we're going to do here is we're going to, and this is the good thing about this very, the Pivot Interactive, it allows us to measure things and create a table. So here I have, for example, let's say time, and it's going to be in seconds, and variable is t. And then here is position. Units are, let's say, centimeters, and variable is x, for example. All right. So then what I'm going to do, I'm going to go back all the way to right an instant when it, cuts the cord. So I'm going to like right there. So you can see, right, it's still at rest, and then it starts sliding down. So I'm going to go like this. This is the instant when it starts moving. And then you can see, right, top right, there is this toolbox. And then you get different type of tools. So I get a ruler and I get a timer. So what I'm going to do here is this. I'm going to take this ruler. I'm going to orientation, make it so that's parallel to my surface. Like there. And I'm going to put that the front of the pack is exactly at my 0, 0. Right. All right. So basically something like this. Now, what I'm going to do then, you can see, right, the timer, I'm going to reset. That means if I start the pack now, I can come back and say that means when the time is 0, my position is 0. Right? Pack is, maybe move this slightly, but, let's say that's good enough. Right? You guys see time is 0, x is 0? All right. Then I'm going to start the motion, and then the timer is synced with the motion now. And it's going to go all the way down. It's going to, stop. Now, what I can do, I can then come back and then get my 0, 0. There you go. And then what I'm going to do, I'm going to then go ahead and measure the position every, let's say, what does it have? It goes until 2.9. That means, so like, let's say I want to have at least 10 measurements, let's say. So maybe I can do the increments of 0.2, right? Or, let's say 0.1 or 0.2 or something like that. So technically I want you guys to have 10 to 15 measurements. So let's say if I go back here, 0, I can then say, all right, so my next time will be 0.1. The next one will be 0.2. The next one will be 0.3. The next one will be 0.4. So I'm going to have you guys go all the way to, let's say, I don't know, let's say 2 seconds, right? So yours is going to be a little bit different because, if you choose a steeper, slope, right, it's not going to take like 3 seconds. It's going to take a little bit shorter time. But let's say right now I'm going to have, I don't know, so see when you come to here, press enter, it gives you more, table. So press enter, it gives you more. So let's say 0.5 and I have 0.6. I think this is good enough for me. That means what I can do from here is this. Then I play the video. I don't need to play, just basically click here and then go forward until the time is 0.1 seconds. See it right now. Remember, I want like, let's say 0.1. There you go. And I measure the position. Well, for me, maybe 0.1 is not good enough because it's kind of slow. So I'm actually going to change it to 0.2, 0.4, 0.6, 0.8, 1.0, and let's say 1.2. All right. Now that means I need 0.2. So then I go and get 0.2. There you go. All right. So one of the things I can do with my computer, which, probably most of you should be able to do, I can zoom in, for example. So I can zoom in and look at the position. So what do you guys think? What is the position of the pack at 0.2 seconds?
Point one.
1 centimeter.
1.1.
Yes. So remember, each mark is 1 centimeters, right? And this is one mark. That means it's 1 centimeter, but a little bit more than one. So I would say 1.1, 1.2. Yes. You guys okay? Okay with the 1.1?
Yep.
If you can't see 1.1, let me know. But this is, I agree with 1.1. So I go there, 1.1 centimeters. Then we go and look at 0.4. There you go. Then again, zoom in. All right, so I don't know about you, but I see 3.8 maybe. You guys okay with 3.8? All right. So then I go and say, all right, so this is then 3.8 centimeters. And I go at 0.6. With 0.6, I think I'm getting 7.8 or something like that. So let's say 7.8. Then when I go to, let me see. When I go 0.8, all right, let's see what we get. So this should be, I guess 12.9 maybe, right? So 12.9 centimeters. So then I go as 12.9 centimeters. If you guys think I'm wrong, let me know. The next one is 1. And I look at it, I would say 19.6, right? 19.6, not quite 20, so 19.6. Again, remember, you're not to use this data. This is just for the demo. So 19.6, and I think I have enough for, let's say. All right, so let's say then you're gonna populate that, right? Go all the way to, let's say, 10, 15 measurements, and you have then position versus time. All right, so now, see if I do then the plot of the, then you have this graph, right? So then what you do here, you click the vertical axis, and then you have options in terms of to select which data column to be your vertical axis. Then you go and say, all right, that I want the position. If there are uncertainties, let's say involved, you can choose uncertainty, but we don't have a table for uncertainty, so we can just ignore that for now. So done. That means my y-axis will be position. My x-axis will be then, let's say for now, let me choose time. So if I choose time, then I get this. So what do you guys think? What type of graph is this?
Parabolic.
Parabolic.
All right, so is it consistent with what we expected? Is this what you
Yeah, look at the
expected?
gravity.
Yeah, because
Yeah.
this is a non-uniform one-dimensional motion, and you're plotting position versus time. All right, so now what you can do here is you can go to, click in this toolbar over here, and you can see, right, it says curve fits. One thing we can do is we can see like what type of curve do we get. So for example, if I do, is it proportional? That means is position and time proportional. So if I click, I get this, which you can see, right, is not a good graph because this data is not proportional. If I go and choose something else, ax plus b, it's a little bit better, but not quite. If I go, for example, and choose y equals ax squared, then I get this. And I think this is, remember, I don't have enough data. That's why you need to have like 10 to 15 data points to have a much smoother graph. So you guys see, right? This is, perfect fit, more or less. Y equals x squared, which is a parabola, right? Is, nicely represent my motion. All right. So now that means one of the things we can do here is we can then understand that if I do position versus time, this is what we're going to do. So then let's say over here, once you collect data, then you're going to answer some questions, right? You're going to answer the questions based on that. And then it's asking to linearize data. Okay. So then it's asking you like a multiple choice questions. What type of graph do you see and things like that. So then let's say again, do you guys remember what do we need to do in order to linearize this? How do we linearize this, this graph, this data?
Use
At
T
a
squared.
time.
Use T squared. Yes. That means we're going to come back, click here to add a new column to the right of this. And we're going to say then this is time, let's say squared like that. Or you can just say T squared like this. I don't know. So units are T, units are second squared, because if you're squaring T, then second also squared. So then this is basically T squared. All right, so now you don't then just take time and the time values, then take your calculator and just square each one of them. The table does it for you. What you're going to do, you're going to click here, and then you're going to go and say change column formula. Once you click column formula, then you have a, kind of like a calculator. Then I'm going to say, all right, so I want in this column, I want to take the column time and square that. This. And I'm going to say, all right, submit. Then what it does, it takes all the values that in the time column and squares that. All right. You guys okay with that? Let me know if you have any questions. All right. Then if you go down, click the time, and instead of the time, if I choose, time squared, then I'm going to get a graph. Well, now you can see, right? My data is position versus time square. My fit was a equals a, y equals ax squared, basically parabola. And obviously this data is not parabolic anymore. So I'm going to go back and change my, fit. So I'm going to say that this is y equals ax. And you can see, right? This is relatively, perfect fit for this type of graph. That means I was able to then linearize it by doing position versus time graph. And then let's say this part of the, second part, right, of the, let's say the lab is asking to linearize data. And then hopefully right now you know how to linearize data and what you need to do. Part 3 is just making sense of the relationship, and hopefully, these are again just some questions that you will be answering based on your particular graph. Okay. And then the last one here is to make a velocity versus time graph, because you're going to make a velocity versus time graph. All right, that means you're going to go back to this graph and do that. Now, here's what I want you guys to do. When you are doing the part 1, remember, part 1 required you to do position versus time. Do this graph, find the appropriate fit, and then take a screenshot of this. And you're going to include the screenshot in basically in one of this, let's say part 2, when it's asking, maybe let's say linearize, right? So you come back here, for example, for part 2 here, for the, question 2 of part 2, let's say it's asking you to linearize it. So here you're going to say that, okay, so I took the graph of the position versus time, and it looked like this, because I want to see how your position versus time graph looks like. So you're going to take a screenshot, and then one of the things you can do here is that, see, let's say when you're answering a question, you can choose an option of to upload a picture. You can click here and upload a picture. That means take a picture of that or the screenshot of that first graph and upload it here, so I have a record of that. Because see, once you linearize, I can't see your first graph because we just have one graph. So that means here you're going to do T squared, and then see the other graph is basically not there anymore. So then you're going to do a correct fit for that. And then you're going to take a screenshot of this and also include in one of those questions. Saying, okay, so this is the plot that I got, and this is what I have for position versus time square. Because the last one is asking you to do the velocity versus time graph. Because once you do velocity versus time graph, I'm not even going to be able to see your position versus time graph. All right. So here's actually probably, interesting thing to see if I, in the future, let's say semesters, I can create multiple graphs. For now, we just have this graph over here. But let's say if you take a screenshot, should be fine. Now, the last one is asking to take this data and use it to plot velocity versus time. If you remember, I told you that linearized graph doesn't help you with that. So we have to go back to the time. Okay, position versus time. That means right now we're doing the last part of this lab, which is doing the graph for the velocity versus time. To do this, one of the things we're going to do here, we're going to make a new column. I'm going to call this velocity. Units are centimeters per second. And it's just basically v as a variable. Here's what we're going to do. I want to kind of do this. If I go back to what we talked about in a whiteboard, if you remember, right, I mentioned that what you do here is you go back to your original, graph, and then you find the velocity as a slope tangent, right, to some instant of time. So the tangent line for some instant of time gives you velocity 1. Tangent at t2 gives you velocity 2. Tangent at t3 gives you velocity 3. So that's what we're going to do. We're going to go back to this graph of the position versus time graph, and I want to have the line, right, this green line, to be only tangent to 1 or 2 points. So I'm going to, you can see, right, this green dots are the data points. I'm going to, if you click on it, it no longer, it deselects that. So basically it's not selected anymore. So if I go and click on this one, it removes the second point as well from my graph. And then third one, it also removes that. So let's say fourth one and things like that. Now, if I do this, see now, this line is now tangent to my point 2 at time point 2. So then if I come back, see, this becomes like x equals at. So 5.5 centimeter per second is then instantaneous velocity, because it's the slope of this line. Because remember, we're doing x equals at, and a is the slope of the line. So then a is the slope of this green line, which is then becomes a tangent to this time equals 0.2 seconds. That means that's my velocity at 0.2 seconds. And I can come back here and say, well, not this one, a second one, right, is 5.5 centimeter per second. Then if I want to go to 0.4 and find the velocity there, then what I do here is I choose this point now, but then I remove the 0. Maybe even remove this point over here. And I'll have this just maybe something like this. Well, it's definitely going to be much easier for you when you have like more data. All right, so let me maybe select this, but not that. I guess if I do the curve as y equals ax plus b, it will be easier because it's not glued to 0. All right, so this is better. So I remove this, I remove that. There you go. Now it is tangent to 0.4, and I get 13.5. So I get 13.5. That means when t equals 0.4, it is 13.5. Right, so obviously I cannot have just 1 point because you're going to get a straight line. So I need something like this. Either those 2 points, or maybe let's say these 2 points. Roughly, you get, 13 or 20, so like that. Now, if I want, this one, then I kind of get, like this. I select those 3, then get the middle one, right? So it's 22.7. That means this is at, at 0.6 seconds. Maybe I can do it like this. It's better because it's exactly tangent at that point. So it's 25.5. Do you guys have question? Are you guys okay in terms of how to find the velocity?
Hi, Professor. I have a question.
ahead.
For the endpoint, should we find the slope from 0 to the endpoint or from the previous point to the endpoint?
Well, I think from the previous better, right? So see, I chose this curve, y equals ax plus b, so that my line is not glued to 0. See, if I do y equals ax, no matter what point I'm choosing, it's always going to go to 0, and my curve going to be bad. So that's why what you do for the velocity versus time graph, right? When you generating the values, use ax plus b, right? And then just choose basically, I imagine like maybe the one after, the next point. So again, more data points you have. So that's why I'm saying like take 15 data points. More data points you have, easier for you to get this velocity portion. So that's why, for example, I can then choose this too. If I remove this, so now see then at 0.8, I have, a tangent at this point. So then I can say it's 33.5. Something like that. All right, so then I think I have enough data points for my velocity. Then I can come back and say, all right, so let's do now the velocity versus time graph and select all the data points that I, ignored before, and this is what I get. And this is actually what you should get for a non-uniform motion. You're gonna get a velocity kind of like straight like this. All right. Because if you're doing position versus time and your actual graph is sort of like a parabola like this, then you can use due to velocity versus time by taking like, let's say individual point, like tangent, 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 and then plot those, and you're gonna get basically something, something like that. That will be velocity versus time. Okay. All right, any questions? All right, guys, so that's all for this. Then let me break you into groups and have you guys work on the recitation too. I have it already posted on Canvas, so you should have access to that. So then take the rest of the time to work on the recitation. So before we start, I want to introduce Paula. She's going to be our embedded tutor. So she will be available during our recitations. And I think she already posted her schedule, right? The tutoring center.
Yep.
So
some students come to see me today, so that was great. Hope to see you guys tomorrow, actually.
Yes, there you go. So so feel free to basically go to your office hours and get any type of help. And she's amazing. She'll be able to help you with everything. All right, so let me then create this. Give you 45 minutes for this. All right, guys, so go ahead and start working on that. Join your groups and start working on the recitation.